Today we're going to be talking about the meaning behind the derivative. So remember from yesterday that we had really two main definitions of the derivative. So remember, our definitions involved limits. This one was more general, at any point x, versus this one was more specific. So at a certain x value that I give you. But remember, the meaning behind the derivative, because these were limits, was the slope of the tangent lines, or the instantaneous rate of change. So those are the two meanings behind the derivative. That's what essentially the derivative stands for. So whenever you hear derivative, think slope of the tangent line. But if I ever ask you for the definition of the derivative, make sure you give me one of these two limit formulas. Okay. It's important for you guys to be able to graph the original function versus the derivative. Now let's look at this. What would the slopes of these tangent lines be? Now these are easy because these are straight lines. The first thing that I challenge you guys to do is look and see where would the slopes of the tangent lines be 0. Wherever your graph is constant, your slopes of your tangent lines are 0. So put in those spots first. I'm 0 for all of those x values. Now look here from -7 to -5, -4. What does it look like the slope of that line is? Well, we know it's a positive sloping line, and I go up 2 over 1. So the slope of that, the slope, and I'm plotting the slope along the y-axis, is that. So notice how when I'm plotting the slopes, those are constant functions. But it's standing for, this tells me from -7 to -4, these slopes of the tangent lines are +2. From -4 all the way to 2, our slopes are 0. Then from 2 over here to 10, what does it appear our slope is? Well, we're negative, and we go down 1, but over 1, 2, 3. So that's going to be a -1/3. Now that's hard for me to draw in here. -1/3 all the way in there. Notice how I have open holes, because at that point and that point, the derivatives are not the same from the left and the right. From the left and the right, those derivatives aren't the same, so the derivative technically doesn't exist at -4 and 2. Now a graph that's maybe a little bit more challenging. Graph the derivative on the same grid. Okay, so we have our original function in there. The derivative I'm going to graph in red. So where does it look like the derivative could be 0, or where our function could be constant, if even for an instant? So notice how I'm increasing, increasing, increasing. What would the slopes, if I were drawing all these slopes of the tangent lines here, what would those values be? Would they be positive or negative? That's what you're looking at. positives or negatives. Here they look like they're pretty steep, but eventually it looks like maybe here around 1 somewhere we go to 0. So I might put a 0 down. Then I start decreasing, or my slopes are all negative until I get to approximately right here where again our slope is 0. So I'm going to put another 0 point down. So notice how I'm putting points down on the x-axis at approximately those x values where it looks like our graph is constant, or where our graph changes from increasing to decreasing, then decreasing back to increasing. Notice how what happens with all of our slopes here, of our tangent lines, are all positive. So all of these slopes here are positive, 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 positive to there. I don't know what those values are, but I know there's some positive value, but they go to 0. Then I go to negative. I don't go too steep to negative, but I go negative sloping tangent lines back to 0. Then we have more positive sloping lines. So that's what the graph of our derivative should look like, and I'll label it f prime of x. A lot of times you're going to have limit questions that are going to be derivatives in disguise, I like to call them, or hidden derivatives. So remember the two definitions I gave you guys. Remember the limit as h goes to 0 of f of x plus h minus f of x all over h. So how does this function kind of resemble that derivative? Well, I have limit as h goes to 0, so that gives me a heads up. I have an h on the bottom. So it looks like this is what I call a derivative in disguise of some function. I need to figure out what that function is and what that value a is that you could be finding the derivative at. Well, it looks like here, with this something being squared, that my function might be x squared. Now notice instead of an x in there, in our x plus h spot, I have a 3. Well, notice if I square 3, that's that value right there. So therefore, instead of putting x's in there, they gave us the actual value there instead of x's, so our a would be 3. Now let's look at the other definition that I gave you guys. Now, what does it appear a is? Notice how in the limit spot for a, and right there, a, we have the number 2. Where f of x is in our formula, they give us the function. So it appears to me that the function's 1 over x, and then just double check that your hypothesis, that the 2 and the 2 there, that are both your a, this last piece here, your function value, is evaluated at what you think that function is, and it is, so therefore our a is 2. And our book doesn't cover these types of questions, so please make sure you understand them, because those have popped up on the AP, and they've been what I like to call hidden derivatives or derivatives in disguise. So you have to realize that these limits are, yes, limit questions, but you can also think of them as derivative questions too. Okay, short video today. Please make sure your lesson summary is submitted on time.